What we're going to talk about now is chemical equilibrium, which is a pretty big topic as well. And specifically, we're going to focus on something called the equilibrium constant for a chemical reaction. You say, all right, well, what is equilibrium and what exactly is this equilibrium constant and why do I care? Okay, well, equilibrium kind of implies that I have a bunch of chemical reactions that are taking place and there's going to be a certain reaction going forwards and a certain reaction going backwards, and they each have a certain rate or speed associated with them. And so what happens at equilibrium is the rate that I go forwards is equal to the rate at which I go backwards. Okay, and so let me give you an example of that you can look at right now. So let's say you had a generic chemical reaction where reactants on the left are making products on the right. Or more specifically, maybe I have a reaction taking place between nitrogen dioxide and dinitrogen tetroxide. So let's say that my reactant is N2O4 and my product is NO2. And so now to balance this, I need a 2 over there. And so I can look at this a few different ways. Okay, maybe I look at it from the point of view of what's happening to the reactants as time goes on, or I can look at it from the point of view of the products as time goes on. So for the reactants, I start out with a pretty high concentration of N2O4, and then it goes down and down and down, and eventually it kind of stabilizes. When it stabilizes is when I reach equilibrium. Now for the NO2, that starts out pretty low and then gets higher and higher and higher, and when that stabilizes, that's when I reach equilibrium as well. Okay, so everything from here on out is equilibrium. The points to the left of this, where things are still changing as a function of time, is called kinetics. And so we're going to focus on kinetics a little bit later, but right now we're just looking at equilibrium. Okay, we're assuming that things are happening slowly enough or that I've waited enough time to be able to reach this state, sometimes called steady state. And the interesting thing is that, at least in this reaction, you can tell pretty easily when you've reached equilibrium because there's a change in color. Okay? The N2O4 molecules are colorless or clear, whereas the NO2 molecules are kind of a reddish brown. And so when it starts out, the solution is colorless or clear. And then as it proceeds and I make more nitrogen dioxide, it turns more of a red-brown hue. So here's the interesting thing. I can compare the amounts of these reactants and products by using something called an equilibrium constant, okay, which we're going to use the letter K to describe. And I'm going to show you now what the formula is for an equilibrium constant. So the equilibrium constant, which is given by capital K, is simply the concentrations of all the products divided by the concentrations of all the reactants. So let me give you a specific example. Let's say I had a chemical reaction with A and B as my reactants, and they're in equilibrium with C and D as my products. When I balance this, maybe I have little a moles of A, and little b moles of B, and little c moles of C, and little d moles of D. The equilibrium constant, capital K, sometimes written KEQ or KC. The EQ just means equilibrium. The C just means concentration. This is going to equal the concentration of the first product, C, raised to the little c power, that's the coefficient, times the concentration of D raised to the little d power, over the concentration of A raised to the little a power, and the concentration of B raised to the little b power. Okay, and so this equation here allows me to figure out the equilibrium constant for pretty much any chemical reaction that I can imagine between reactants and products. So let me give you some information about this equilibrium constant. Okay? This equilibrium constant, this K, is really meant to give me some sort of idea of how well the reaction proceeds. Okay? It doesn't really tell me anything about kind of how fast the reaction is happening. It's just telling me sort of how easily it takes place. So if the equilibrium constant is very big, if K is very large, okay, that means that the reaction proceeds nearly 100% to completion. So I have way more products than reactants, which makes sense because then my numerator is a lot bigger than my denominator. If I have a very small number for K, that means that the reaction barely happens at all, right? So the amount of products I have is really tiny compared to the amount of reactants that I have. Every single chemical reaction on Earth is really a reversible reaction. That means I can go forwards and I can go backwards, and it's kind of doing this all day. But even though that's true, in practice, a lot of reactions have super big equilibrium constants, like greater than 10 to the 10th or something, which basically means that I have like 10 billion times as much products as reactants. And so I can assume that these things are irreversible, that they only really go in one direction. The other thing I want to point out is that this equilibrium constant, this K, is a dimensionless quantity, because even though it looks like I have concentrations on top and concentrations on bottom in this fraction, each of these terms is really dimensionless because I'm dividing by a reference concentration which I set equal to 1 under standard conditions. A little bit more information on this equilibrium constant. Okay? The K is telling me something about what's called the thermodynamic stability of the reactants and the products. It doesn't tell me anything about how fast the reaction is taking place. I have zero information about kinetics. Okay? That's coming up next when we talk about that in another module. Okay? However, I will say here that there's usually some kind of delicate interplay or relationship between kinetics and thermodynamics. So now let's look at what's called heterogeneous or heterogeneous equilibria. This is where I have a chemical reaction with different phases that are present. Very often you have gases, maybe solids, maybe liquids, and they're all in there. So if I have multiple phases present at the same time, you might think that this would complicate my expression for K, but it's really not that bad, okay? Because when I look at pure liquids or pure solids, their activities are effectively 1, right? The concentration of a pure liquid in itself is assumed to be 1. Therefore, I ignore it in these equilibrium expressions. The only things that I have to worry about for an equilibrium constant are gases and or aqueous solutions. That's it. No pure liquids, no pure solids. Okay, makes my life much easier. So now let me tell you something called Le Châtelier's principle, which was discovered in the 1800s, late 1800s. If you have a system at equilibrium and you disturb it, okay, you alter it somehow, Le Châtelier figured out or proposed that what's going to happen is the system is going to try to go back to its original state to alleviate the stress that was imposed on it. Okay, and so what are these disturbances, right? How can you shake things up? How can you mess up the equilibrium? Disturbances include things like changing the concentrations, changing the pressures, changing the temperatures. All of these disturbances are temporary, okay, except for temperature, okay? When you change the temperature, that's going to alter the equilibrium permanently. Everything else will revert back to its original equilibrium point eventually. So let me show you what happens if I disturb the system by changing concentration, for example. If I change the concentration of one of the reactants, then when I look at my reaction quotient, which is really products over reactants, okay? If I'm increasing the concentration of the reactants and the reactants are in the denominator, that means that my Q, my reaction quotient, is going to decrease. If it's going down, that means that either the numerator is too small or denominator is too big compared to what I need at equilibrium. Okay? Either way, I have to change things, okay, to try to fix it to go back to equilibrium. So to go to equilibrium, I have to make my numerator bigger and or make my denominator smaller. Either way, I'm going to use up some of these reactants and convert them into products. Okay, and so I would say that the reaction shifts forward or to the right to achieve equilibrium. If I look at a different situation, like if I decrease the concentration of something. For example, a product. Let's say I was decreasing the concentration of one of the products. Okay? Maybe I remove it from the reaction mixture as I'm creating it. Okay? Then the system is thinking, wait, what just happened? I thought I made some product, but I don't see it here. Oh well, I guess I'll just have to make some more. Okay? My reaction quotient, my Q, still went down, but the reaction is going to have to go to the right to try to make up some of this extra product that I lost by sort of taking it out of the system. So as a general rule of thumb, you want to do reactions so that the concentrations of the reactants are the highest, but this isn't always possible for obvious reasons, things like economics or availability or safety, things like that. Now let's look at some other disturbances, like if I change the volume of the container. This only really affects gases. If I have a reaction that's including gases or involving gases, then volumes are going to be inversely related to concentrations. So if I decrease the volume, that's basically the same as increasing the concentration. So I can think of volume changes as being related or the same as concentration changes. Because I want the highest concentrations, that means that I typically want to do these reactions in the smallest containers that I can. However, you have to be careful because if the volume is really small, that also means that the pressure is going to be very big. Right? Pressure and volume are inversely proportional to each other. So you have to make sure that everything is safe and that the container can withstand these pressures that you might be creating. So now let's look at pressure. How pressure affects the reaction will depend on how exactly the change in pressure takes place. If I'm dealing with liquids or solids, these are fairly incompressible, which basically means that these reactions are not going to be affected by changes in pressure. But if I have gases present, then things will matter. Okay? If I change the total pressure by, for example, decreasing the volume, then we talked about that already, right? That's the same as concentration. If I increase the total pressure by changing the partial pressures of one of the components, then the reaction is going to shift in the direction of fewer moles of gas. So I can't say that it goes to the left or that it goes to the right, but whichever side has the fewest moles of gas in the balanced chemical reaction. If I have a higher pressure of one of these gases, that means that I have more moles of it. And if I have more moles, they're going to have to occupy greater volume as before. Okay, and so the idea is that the system is going to want to have as few moles as possible in the same volume, since the volume is proportional to the number of moles. Another thing that can happen is I can change the total pressure by just adding some kind of inert gas, like something that doesn't take part in the reaction. In that case, even though I'm changing the total pressure, the equilibrium is not going to be affected. Okay, and so in order for the pressure to actually have an effect, that substance has to actually be part of the chemical reaction. What if I had a catalyst? Okay, a catalyst can help to speed up the course of a reaction by giving me some kind of alternate pathway for the reaction to take place. Even though this is going to affect the kinetics or the rate of a reaction and make it go faster, it's going to have absolutely no effect on the thermodynamics or the stabilities of the products or the reactants, so it's not going to affect the equilibrium constant at all. Okay, temperature is a little tricky. Temperature will permanently affect the equilibrium constant. In order to know what happens with temperature, I also have to worry about enthalpy, delta H, for the reaction. Okay? If the reaction is exothermic and delta H is negative, then increasing the temperature is going to make the reaction shift to the left. Okay? Think of the heat in an exothermic reaction as being one of the products. So if I increase the heat, I'm increasing one of the products. The Châtelier says to get rid of it, I have to go to the left. If the reaction is endothermic, then the heat is on the right-hand side, the reactant side. Increasing that is going to make it go to the right. Okay? And so this is the only thing that will permanently alter K, the equilibrium constant, because it turns out this equilibrium constant isn't really truly a constant. It's actually a function of temperature.